In our properties, we have the velocity function, we have the position x, we have lane position, lane number, re-entry, type, carbon emissions, and fuel consumption. For our constructor function in the methods, our velocity is chosen randomly, our lane number is also chosen randomly per car. The position starts negative 10, which means before they enter the GUI, and then we have 0 for re-entry. Our type is also randomly decided between 1 and 2, so we have two different cars, since we have two different cars. As for carbon emissions, we start with 0, and fuel consumption 0, and lane position 0.
Initially, to choose lanes, we do a random integer between 1 and 5, and then we use logical indexing to say if it's chosen lane 1, its lane position, or the y factor that will be plotted in the GUI, is 0.2 or 0.7 or whatever respectively. After that, we need to tell the system what does type 1 and type 2 mean in terms of the calculations, and this just assigns the proper data that was given in the assignment to the proper cars for calculation later on.
The function emissions pretty much does how to give the output data. So once again, you have the object carbon emissions, the factors, and the velocity times 10, which would be to even out the scaled down version of the velocity by 10. The function fuel usage gives us the if and else if statements, which are given in the data of the assignment. We scaled it once again down for the velocities by a factor of 10. And at the end, you would have the function to get the fuel usage.
As for the movement, we have the position of the object, as well as we add the velocity of the object to calculate its movement across the screen. For get points, we simply refer to the object's location, and for getting its velocity, we refer to its velocity.
Reset position takes over once a vehicle crosses beyond the visibility in the GUI, and it will reset the X position of a car back beyond the GUI, a set amount, and then a random other distance to determine the random reset time. The velocity will also be randomly chosen just as it was before. We chose a -33 initial offset to allow the on top function, which we'll go into next, to split up any potentially stacked cars before they enter into the visible traffic simulation.
As for the on top function subtracts 1.35, which was calculated experimentally, from the actual position of the object if one car is on top of the other car before it enters the screen. For lane change up, this function adds a 0.5 in the y direction, which is our difference between a real line number. So our numbers go from 0.7 to 1.2 and so on. So from 0.7 to 1.2, we need a difference of 1.5. Therefore, for lane change up, we have a 0.5. To lane change down, it's the same exact thing, except this time we see the object's lane position and subtract a 0.5.
Now we're going to run through our automatically generated GUI code. So as you can see here, here's what you get when you use guide to create your GUI. When the GUI opens, this chunk of text up here plots out the road for us. Then it creates the initial objects that will be plotted once the user hits start, staggers out the objects, and then stores them within a user data handle so it can later be picked up by the start button function. Okay, here in start we grab the data that was initially stored at the open. We grab the state of the start function, which is either 1 or 0, pressed or unpressed, and we also pull in a fuel and emissions array for use in plotting data later within our function. Everything is wrapped in a while loop contingent on the start button assigned to Z being pressed. we set up some empty variables for lane position, X position, emissions, fuel, velocity, just as was done in Greenball. We then reiterate the axes before we start plotting a whole bunch of stuff. So we use for loops with our object-oriented methods, and using the same method as Greenball and Colorball, we create an array for the L positions of each ball, the X positions of each ball, and the velocity of each ball. Down here you see our first velocity check and a position check, which allows us to make the slow down collision prevention function work. Right below that, here is our longest chunk of code, and that's our lane changes. We decided to give the cars a 7% chance of changing lanes, and this is also contingent on if the car is visible. We don't want our cars jumping around off screen, because that would create more issues than it would help. I'm just going to go through for one of the middle lanes, since the same logic applies to all of the other lanes. We decided to hard code each lane just to be 100% sure everything was working, since we've been snagged up on this system for a few days now. So if the vehicle is in the assigned lane, check the lane below. Find the position of all X cars in the lane below, and of those cars in the lane below, find them within this range of the car being checked. If nothing comes up, then you can lane change down. Else, check the lane above using the same logic. If there's nothing above within that range, lane change up. If none of these come true, the car simply won't change lanes, and it'll skip past the rest of the lanes. After the lane change, we need to reassign L in the array to the new position, so that the rectangle command later will plot it correctly. Now here's another double for loop, which shows our on-top function, which will only work when the position of the car is off screen. We're using this to compare the X position of two separate cars, and then using a little bit of logic, we determine if they're too close together, and if so, we fling them apart using the on-top function previously shown.
As for the stop or collision avoidance function, we can still use the A value, which was assigned here, the car of X of B and minus X of C. And for the lane change, we look at it in a specific distance from the center point of car A, and to -8 8 points behind the car A, and then if both of the cars in the same lane and they're about to, car B, which is behind car A, is about to enter this zone, then what's going to happen to car B is they'll slow down by a factor of 0.3 miles per hour. And what's going to happen with car A is it'll speed up by a factor of 0.1 miles per hour. As we said, to avoid traffic jams, we have also said that any cars that are below 54 miles per hour, which is 55 miles per hour, then please bring it back up to 55 miles per hour. This is to avoid traffic jams. As far as plotting the rectangles, we have a for loop which goes through, which first just looks at the type of the car that was decided randomly by our object-oriented program. Then we use the rectangle command, and based on the position of the object, which is XB, and LB, which is the Y position of the object, we give it a specific height and a specific width. And then we decide a curvature to make it look more like a car. Finally, we give it a face color to distinguish between the two different models. And same thing applies to the Type 2 car, which is the Golf. Volkswagen.
The object's type data calls up the data given in the project. There is we call upon the function in the traffic simulator, object's B emissions, as well as the object's fuel usage. Then we put all the emissions from the vehicle into arrays in order to do the sum and get the cumulative instantaneous rate for emissions and fuel. Then we display it as a string and is set to be shown in the GUI.
The last piece of the puzzle is another check for on top. The two final pieces of our start function show another on top function just to make doubly sure that nothing is stacking on top of each other. And the last piece of the puzzle is blacking out the cars to prepare it for the next iteration. This is the easiest way we found to prevent the rectangle function from tracing along the vehicles. The last chunk of code you see is 1 over talk, which basically says what is the frequency or the frames per second at which this loop has run through. And then we display that in the top right corner of our GUI. The stop function is what allows us to reset our code. So when this reset button is hit, it'll redo everything it did at the beginning and also reset the cumulative fuel and emissions data. It'll then, again, store these in the start user data shelf. This last bit of code here allows the user, when the simulation is paused, to view the different data points for instantaneous carbon emissions and CO2 in plots, just to see how the simulation has been functioning over time. Our last point about the functioning of this system is while the system is continuously tracking 20 cars, because the system has to stagger the cars apart and there is a random re-entry time, the chance that all 20 cars will be visible on the screen is fairly slim. And again, because of the randomness, the density of the vehicles is going to fluctuate. Even though a car is off screen, it is still moving and still factored into the calculations, which was a stipulation of the project statement.